Hello, Year 7, and welcome to Week 2, Lesson 4. This is our second lesson in the sound topic. So it's Lesson 2 of the sound topic, and this is titled Sound and Energy Transfer. So the things that we need to know by the end of this lesson is how to describe how sound is produced and travels, how to explain why the speed of sound is different in different materials using particles, how to contrast the speed of sound and the speed of light, and then last but not least, how to compare the time for sound to travel in different materials using the data given. You're going to need a calculator for this lesson. So have a look around on your desk and see if you can pull up a calculator. If you don't have a calculator, pretty much every phone these days has a calculator. So grab your phone out and turn it to a calculator or open a calculator. Gosh, I feel old. And then let's start the lesson. So first things to know is that sound is a vibration. So this vibration is something that moves back and forth. So sound is a vibration, and it's transferring its energy via a longitudinal wave. So if you remember from yesterday's lesson, a longitudinal wave is a wave where the particles compress and then spread out, or rarefaction is the part where they are spread out. So those particles are moving backwards and forwards. And so sound energy is transferred from the source to the receiver. So the reason you're hearing this is your laptop or computer is transferring energy and your ear is receiving that energy, that vibration through the air. So we've got our particles moving back and forwards and our energy moving. Okay, and remember, if it's a longitudinal wave, which this is, the particles move parallel to the movement of energy. So particles are moving back and forwards in the same direction that the energy is traveling in. So our sound waves, they spread out from their source. So if I yell, hello, my sound, that sound wave is spreading out. So if you're 100 meters from me, you would not hear that because the sound wave has spread out so much, you would not be able to hear it. So sound travels from particles colliding with each other and transferring energy. So it is particles colliding to transfer energy. So when I speak, my voice box is creating air particles to hit each other, and then that air particle will hit another air particle, which will hit another air particle, which will hit another air particle, which means that that sound will transfer. It's particles colliding with each other. So sound is slowest in gases because the particles are so far apart. They're about particles colliding into each other. And so because they're colliding into each other and they're really fast, spread out really far, they take longer to collide into each other, which means that sound transfer takes longer. If you picture 10 people and you want to pass a ball from the first person to the 10th person, if everyone is standing about half a meter away from each other, they can just immediately, without moving, pass it to the next person. But if you then spread those people out, so they're all standing 10 meters apart, it takes a lot longer to pass that ball from the first person to the last person because they have to move further. That ball has to move further before it passes from one person to the next. So the speed of sound in air is therefore only 340 meters per second. So if you were exactly 340 meters away from me and I clapped my hands, it would take exactly 1 second for that sound wave to reach you. So that's the speed that sound travels in air. So if you see a plane in the sky, the reason you see the plane before you hear it is that light travels a lot faster than sound. So the particle there at the top will pass its energy by colliding or vibrating and then colliding, and therefore transfer the energy to the middle particle, which will then transfer the energy to the last particle. So in liquid, the particles are closer together. So sound waves, therefore, they can travel faster. In fact, they can travel 1,500 or 1,500 meters per second because the particles are much closer together. So just like that ball analogy, they're able to be passed much faster. And then last but not least, sound travels the fastest in solids as the particles are connected. They are all touching each other. So the sound travels at 5,000 meters per second. Still nowhere near as fast as light, which we learnt was 300,000 meters per second. But 5,000 meters per second is still not slow. So the energy is still transferring by particles colliding with each other. So, space is a vacuum. There are no particles in space. And so because there's no particles in space, sound cannot travel through it. So there is no sound in outer space. So all those Star Wars movies you've ever watched, where you hear all the gun battles and the lasers and everything, are absolute rubbish. I mean, the movies are great, but there wouldn't be any sound in them because sound does not travel in space. There's no particles to physically collide with each other. And because there's no particles to physically collide with each other, there is no sound. So if we were to make a vacuum, a place that is there where there is no particles, there would be no sound in that vacuum. So at the end of this video, there is going to be a little demonstration of a bell in a jar. But in this jar, we're going to suck out all of the air, and therefore you won't be able to hear the bell because there's not going to be any particles to be vibrated by that bell. If you want, Google as well or look in YouTube after this video and have a look at Star Wars without sound. It's quite an interesting and funny video to watch because it's actually accurate. There would be no sound in that battle. So, speed of sound. Sound travels about 340 meters per second in air. So speed would be faster in liquids and solids, as we've discussed just then. So using time and distance, we can actually calculate the speed of sound. And as a fun fact, we see lightning before we hear thunder because the light is much faster than sound. It's 300,000 meters per second as opposed to 340 meters per second. So, we're going to learn and work out how fast sound travels. So to calculate the speed of sound, we can use this triangle. Distance, speed, and time. So D is the distance, S is the speed, and T is the time. So we're going to be using lots of triangle formulas in physics. So we need to know how to use them. So how it works is that whatever one you want to solve, whether it's distance, speed, or time. So for example, if the question asked, what is the distance if the sound wave that travels 340 meters per second takes 2 seconds to reach us? We want to solve for distance. So in that question, we would cover up the D and the formula would be speed times time equals distance. So if we want to work out how to calculate speed, we cover it up on the triangle like that, and we get distance divided by time. So write down that triangle and then write down that formula. Then can you work out for me what the formula would be for time? So time equals what? And then can you work out what distance equals? Distance equals what? What are those other two formulas? Pause the video and have a go at that. If you didn't manage to do it, if we want to work out distance, we cover it up and it is speed times time. So write down that formula if you did not get it. Make sure as well you are writing down the units. It is meters per second, not miles per second, as some of you might have thought, and time. So meters per second, and seconds. And then last but not least, time. You did distance divided by speed. You are correct. So well done there. So we can calculate the speed of sound. So what would the speed be if distance is 50 meters and the time is 5 seconds? What would the distance be if what would the speed be if distance was 10 meters and time was 10 seconds? And then the next two I want you to do is what would the speed be if it was 3? So what would the distance be if the speed was 3 meters per second and the time was 15 seconds? And number 4, what would the distance be if speed equals 10 meters per second and time equals 2 minutes? Pause the video now and have a look at those 4 questions and write down the working out, your answer, and your unit, please. So you need to include in all 4 of these, working out, answer, and the units it would be in. If you got 10 meters per second, 1 meter per second, 45 meters, and 1,200 meters, or converted it to 1.2 kilometers, you are right. Well done. If you want to watch an interesting video of a man breaking the speed of sound as he's parachuting, Google Felix Baumgartner or Google, I think it's Red Bull, and then his name, and you can watch him parachute from the edge of space and break the speed of sound while parachuting. So, we can actually represent sound using an oscilloscope. So, a constant sound would appear as a simple wave pattern that remains the same. So at the end of this video, there's going to be a demonstration of an oscilloscope, and we're going to change the amplitude and change the frequency. So sound that's not constant, so for example, we'll have a wave that will change, like the image on the PowerPoint. So an oscilloscope can just represent sound waves as a transverse wave. So if you want, have a go. There's some brilliant software online where you can play around with online oscilloscopes. So Google oscilloscope and have a go at an online oscilloscope, changing the volume and changing the pitch. So changing the volume and changing the pitch, and we will learn about more of that in lesson 3, which is lesson 1 next week after your Easter holidays. So make sure you've watched this video. Keep watching as well, because at the end of this video, there's going to be a number of different experiments that we're going to have completed to show you how some of this works. And then there are 2 worksheets for you to do. Once you've done those worksheets, can you make sure you are uploading them onto Show My Homework so that we know you are completing these lessons, please? So make sure you complete the worksheets on a Word document and then upload them onto Show My Homework. Keep watching this video for some fun experiments that we do. Otherwise, take care, and you'll hear from me Monday, first week back after the Easter holidays. Well done. I hope you're enjoying this sound topic, and always remember, stay safe. What we can see here is an oscilloscope where we can see the difference in amplitude and frequency. So if I increase the amplitude here, the wave gets higher because amplitude is from the center of wave to the peak. And if I decrease the amplitude, the wave gets shorter. Now, we can also change the frequency. So the frequency is the amount of waves per second. So if I decrease the frequency, the waves are very flat and very long, and they've got a large wavelength. And if I decrease frequency, the wavelength decreases. So as we can see, we've now got very short wavelengths with a higher frequency, and a lower frequency, we've got a longer wavelength. But if you notice, the amplitude does not change.